Welcome. In this session in linear data analysis, we'll explore the scatter matrix of data. Let's remember that our data are gathered in a matrix A. These are all real numbers, there are m observations, and there are n variables in our data. And m is the zero mean form of A. The scatter matrix is defined, we'll use the symbol S, and we'll define the scatter matrix as being the transpose of the zero mean matrix times the zero mean matrix. And the only difference between the scatter matrix and the covariance matrix is that the scatter matrix doesn't include the division by one less than the number of observations. And because of its construction, this is symmetric by construction, and if the zero mean matrix is full rank, this is positive definite, and if M has some linearly dependent columns, then this matrix S is symmetric positive semi-definite. And because it is only a scale factor different from the covariance B, so S has the same eigenvectors as the covariance matrix B. And we were writing those as eigenvector 1, eigenvector 2, and so on. And the S also has eigenvalues that are closely related, eigenvalues that are scaled. So these are lambda j was the jth eigenvalue for the covariance matrix, and if we just multiply that by m minus 1, then we get the eigenvalues of the scatter matrix. We won't need the eigenvalues very often. We'll be mainly exploring the eigenvectors of the scatter matrix. So you can think of the scatter matrix as, so S is, you can think of this as being the weighted covariance. And the reason for weighting it is that it allows us to take into account the number of data. Sometimes with covariance we want to remove the number of data from our computations because we want to understand variance and covariance, and sometimes we want to include it. So this gives us the mental flexibility of doing both. So let's recall the spectral theorem. And this incredibly useful theorem says that the eigenvectors of a symmetric matrix are an orthonormal basis. Normal basis for all of the vectors that have n entries. And that's the geometry, so that's from the spectral theorem. The algebra of this is that we get, I'll say, better, in quotes, coordinates. Because if the eigenvectors, or the loading vectors, are a basis, in some sense they're a better basis than just taking, in the case of our zero mean matrix M, we have more observations than we have variables typically, and so it's difficult to select a set of n that are linearly independent and provide anything like a good basis, but the eigenvectors are a good basis. Now the geometry of these is that these describe axes, describe new coordinate axes, and that's the sense that is interesting me right now. So what can we do with these when we combine them? Well, what we'll do is we'll start to understand how we can use these as scores.